so his response to that was
I want to look into the microphone.
To, like, an evil version of himself with like a Joker like banner. Right? Really funny.
I have a funny story, sort of funny.
Can I finish mine?
I got a lot of things to say.
That was the end.
No.
Interrupt the story mid-story.
This lecture is starting 15 minutes late. Because the lecture was 15 minutes late.
Some guy's like, oh, so doxing's funny? Then I'm about to be hilarious. And just dumps his entire shit.
Please let Dr. Aruji know.
Name, his social security.
Please let Dr. Aruji know.
Coordinates, all of it.
Wait, his social security?
Yeah, and so
the internet's fucking wild.
Yeah. And so literally what happened is like, you know how he has like his merch, right? And he has the mask? That's his brother. Homeboy's built like Tim Bazzelli. Like,
the dream is?
Yeah.
That's wasn't this like a year ago or something?
It was like a couple days ago.
Because I remember
it felt like a year.
Saying leaked in the picture dream that was like a year or so.
I don't know why you have to do T-Buzz like that though.
True.
Can I tell my story now?
It looks like the same like it looks like his profile picture though. That's what I'm saying. Like it's the same framing.
Can I tell my story now?
Yeah, sure.
So yesterday, for some reason, UCF decided to highlight a particular student at UCF who was apparently the youngest undergraduate student. And it was some girl, I don't even remember her major, but she's 15. And it's
What
like,
the heck?
Andy's 15.
Andy,
what the heck?
He's 15 and he's a
grad
student.
So must have missed out just on 5
Let's all
months.
bully that 15-year-old.
All right, well, today's lecture is from Seba. Yay! And it's on things to do with Convex.
So this is him, like...
yeah, now let's move forward.
Whoa, no, let's not move forward.
Yeah, it's later.
Yeah.
This is the lecture.
All right, you're losing much.
Yeah, I know. Today's the shorter one.
Okay.
Convex Ultra?
Alright, so let's see. So where are we going to start?
We'll start my lecture with What is the lecture topic?
Alright. Let's start with C. We'll start with this. Alright, this one, people at the camp remember this one. But we're just gonna go through this one kind of quickly. I'm not gonna talk about the solution.
Is where we could put 2 things down?
Yeah, favorite upsolve this?
This problem statement is so long.
So this one, hiring help. You work for a certain large unnamed software development company with 10 developers, and what's going on is like each of these like coders has like number of lines of code and then like number of bugs, right? And so when you need to like do a project, right, you can like allocate like hours of like people's time, right? Like if you're gonna like say like maybe it'll take like 10 hours of like people like working to like do this project, right? You can like split it up, you know. 9 women can have a baby in a month.
This is like worse than had they written no flavor text at all.
Yeah,
They should have just omitted like this garbage flavor text.
Yeah. So it's like but yeah, so you can like allocate like the like if you have 3 coders, right? Then like you can allocate like the hours between the 3 of them, and then now like the number of lines of code will be like the time times their like line of code rate, and then like the bugs they fix is like the time times like the bug rate, right? Mm-hmm. And so that's all fine and dandy, but now there's a hiring freeze, and so they want to bring in like an external consultant, right? And so the consultant is gonna write like a fixed number of like lines of code, and then like a fixed number of bugs. And they've got like T hours to do it, right? So what you want to know is like, okay, like say it takes like this consultant like this long to do like this many lines of code and this many like bugs. If like you can already do that with like your coders in like the same amount of time, then you can't hire the consultant. That's the idea. Like you can't hire the consultant unless it's like unless like they're like better than like any allocation like you could do, right? And so now you want to know like which of these like consultants you can hire. And then you have to process requests, like process things that are like, this person is, like either you have like a certain consultant, like, you have either a certain consultant or like a certain person quits the company. You don't have any ads, you only have like people leaving. Yeah, so that's the problem. We're not going to talk about this one a whole lot,
True, but
but
where's the quiz?
kind of open the gates of this one just so it doesn't like spoil the rest of the rest of the lecture doesn't spoil this one. But this one's basically like, all right, so we're gonna reverse these and do ads because removing stuff is like literally always hard.
Like, did we solve this one? Did we solve this one?
Not in contest.
Wow.
Save up, so did we?
Yeah. This one was yeah. So.
Do we run this? See the fast Fourier transform.
Alright, so yeah, so we're gonna reverse the queries and process like adding people because removing people is like always hard, right? And so when you look at this, right, and you see like this thing, you see this shit, you see this, and you see like these two metrics, you should be thinking, man, is this geometry? And the answer is yes. This is like the whole reason I started with this one is like this should trigger like geometry alarm bells in your mind. When you see like this stuff where it's like you can give like them like any like allocation, like any real like allocation of people, and like you can like kind of like do like a linear combination of them. And like yeah, so basically what's gonna happen is like say we have one coder, right? This is gonna be like L and this is gonna be B.
I predict.
If we have one coder over here and another coder over here, then where's that ruler I stole from Jacob's locker? Yeah, if we have these, then anything on this line, we can actually we can also achieve, right? Like by like the hour allocation thing, right? So the result of this is we want the convex hull of the coders. Coding hull, if you will.
I won't.
So let's look at these now in this. So if we take these guys, like the consultants, and we divide like their lines of code and their like bug fixes by T, that gets you like their like rates, right? Like their rates of like fixing stuff. So you can like divide it by T and then get their rates, and then now you want to know, hey, for this like person, like can for this person, can we for this person, like, is this better than like all of our coders, which is equivalent to saying, hey, is this consultant in or out of the Convex hull? Right. So yeah. So that's kind of where we're at, right? So now we need to know, we've got a Convex hull, and we want to know, hey, is there like a point like inside of here? So our hull kind of looks like this if we have like these coders.
Like the Convex hull represents like all the possible combinations of rates we could achieve with our coders.
Yeah.
Hey, it's pretty good. That's a pretty good hole.
Alright. So then
Nice
now
Nice hole.
we've got our hull.
That's a
Nice
snap.
hull, right? If you've got a consultant out here, right, then you know we can hire them. But if it's like over here on the line or inside, we can't hire them.
So
you get
true.
X.
Saba,
So true.
did you talk about why you drew the line to the X and Y axis?
Oh yeah, this line is horizontal and this line is vertical because like if you have like this allocation, you can also make like this like if you can make like any coder like not fix any bugs basically, right? So it's like and you can make any coder not write any lines of code. So it's like
Like a point that's strictly above or strictly to the right of some other point is strictly better than that point.
These are just the coders, not the consultants, right?
yeah, these are the code.
You can always do less, but you can't do
Yeah, you can always do less, but you can do more. Like in this problem. So in this problem, the last lines go like this. That's not always the case, but in this problem they do. And so yeah, so
So
now now we want to know, like, okay, we've got a hull. How the frick are we gonna go ahead and actually like how are we gonna do this? How are we gonna like find if it's in there?
Search.
Is there a hack pack?
There is hackpack, but we're gonna talk about a couple different ideas that are pretty powerful. So this one is gonna be one that I talk about. And generally, I think like convex hull, you should just like hackpack, but some of these convex hull ideas are pretty worthwhile. So let's go ahead and draw ourselves a nice hull. We're gonna draw ourselves a nice meaty hull.
Wait, but the one in the problem is nice because it's like X and Y axis, and everything's positive. Like everything's in the first quadrant.
Yeah. But we're gonna talk about like the general case one.
Yeah.
Because the way you like maintain it for this one is different because of the other queries you have. Right?
Yeah.
So what we're gonna do is like say we've got our polygon, right? We have it sorted in like counterclockwise order. Let's go ahead and triangulate it. So what we're gonna do is we're gonna fix 0, like the first point, and we're gonna split our thing up into all these triangles, right? And so now, say we've got like a query point, right? Say we've got a query point. Say our query point is like, I don't know, let's say it's like right over here, right? What we can always do is, alright, so does that, who took like physics in high school? Raise your hand if you took physics in high school. Alright, so there's this trick I learned in high school physics, right? It's called the right hand rule. It's really, really useful.
In physics?
Yeah.
E and F?
Yeah.
Okay.
You should be learning it in physics one,
Well,
also for torque.
So
Bartfeld did that.
you're gonna trigger your like inner like James Bond. You're gonna go like this. But the way it goes, it's like this. You go like
Gang signs.
like this. Oh no, that doesn't help.
Different, right?
It was showing their
So you're gonna go like index finger, middle finger.
We already
thumb
talked
finger,
about
right?
this in the
Make sure
lecture
you
that
use
you
your
weren't
right
in.
hand.
Oh really?
Yeah.
Oh, that's fine.
Got it. That's so sad.
But yeah. So right hand rule, right? So if we have like one of our lines, right?
Are you cross product?
Yeah, if we have one of our lines and one of our like query points, right? We can determine if this query point is like to the left or the right of the line, right? So that means that if we fix this point, we can find the rightmost like red line that is to the right of our query point, right?
Yeah.
So if we can find that, then that means that we know if we find the closest red line to this point right on the right, that means that it has to be inside this triangle.
But what if we had the upper and lower holes and
Mhm.
binary searched between those?
I mean, you could probably, but this one's just one, which is pretty nice. Yeah, I don't really know how the upper and the lower look. Like, I never do like upper and lower holes, so I don't really know.
I see.
Yeah, that seems to be like harder to do too.
But yeah, so you've got the hull. You can find like the closest point under it with a binary search, right? Like we say, like, okay, is it like on the left or on the right, right? And then once we find it, once we find this triangle, now we can do like, is this point in this triangle? Which we can do with like 3 cross products, right? We can say like, hey, we have our point. We have like 2 vectors here, right? And we've got our point. And we want to know, hey, like if this is A, B, and C, we want to know, is it to the left of AB? Is it to the left of BC? And is it to the left of CA, right? So you can do 3 cross products to see, hey, is this point like in this triangle?
Isn't it possible to do this with just one cross product with like if you just make sure the point's to the left of B to C, and then if it is, then it's inside like assuming the
Well,
point's
no,
to
if
the
it's to the left, if like we know it's like We know it's like
Oh.
in here,
Like, we
but
know
yeah,
it's
I guess you need to make
Well,
sure
for-
that it's inside here.
I
So,
don't know
yeah.
for the problem.
You can do it like for this problem because you know it's inside like this left bound and inside this right one. You can check like just this top line, but I usually just write a function that does the 3, just because it's like convenient.
Safe.
But yeah, so now you've got this triangle. You want to check if it's in here, and that's how we find our point. But yeah, if you're careful about it, you can just check this top line, check that it's like inside like this line, so that way, like if you have a point over here, right? If you have a point over here, you're still gonna get this part of the like in the binary search, right? Like if we have a point out here, it'll give us this triangle in the middle. So we need to make sure that that it's actually like inside this line. So with our coders, we can do just that, but the problem is we need to add people, right? And so there's a couple things we can do. One of them is if we're reversing our queries and we keep all of our what do you call them? All of our, like one thing we can do is like all of our like coders will be activated for like a certain range of time. So one thing we can do is do like the segment tree on time thing, and then have like a convex hull in each segment tree node, and then for each of our queries we check like all the convex hulls on the way down. But the problem is that like that doesn't work. So the thing is, like, you might have like one segment tree node up here that has like one really good coder, and then another segment another node down here that has the other really good coder, and those two coders, like as your allocation, are like where this guy lives. Like your consultant might be on that line, but because like sorry, I was up here. So if you have like maybe you have like one coder that's like 100 0, and then here you have another coder that's like 0 100, right? And then if our query is like 50-50, then if we do like if we have this, right, then this convex hull would have 100 0, this convex hull would have 0 100, but none of them would have both, and so it would be in neither convex hull. So unfortunately, you'd have to process like actually adding a point to this hull, which is doable, but it's kind of toxic. I don't really want to talk about it, so we're gonna move on.
Wait.
Yeah, but you should have this in your hackback, right?
No, I don't. This is the only time I've ever seen a problem with that.
I've seen a lot of problems.
Wait.
Wait, what?
Like
There's too much
convex
for it.
hole where you need to add.
I'm about
we
to
used to
talk
have this
about
in
that
the
exact problem.
Adding a
The
point
problem
to
I think you're
function.
talking about, the Smock problem. But what was it like?
Oh,
Oh, it's wrong for you, Joe.
I was thinking you could just like since of the constraints of the problem. If you have like first you check the points inside the convex hull, and if it's inside you don't have to add it. But if it's outside, you can like do like a binary search to figure out like the uppermost point it should hit and the lowermost point. Cause, like, you know,
Yeah,
the points here
that's
go
what you do.
Yeah, it's like that. It's like
You keep it as set. You don't actually even need to do a binary search because every point's going to be removed at most one time. So you can do a linear sweep and just keep removing points if that point is convex or concave.
The
So save
Java
yourself some
hackback
time.
has it.
Yeah, it's like it's not super like it's like I'll talk about it if we have time, but it's like
You have to make sure to start that linear sweep at the right place.
that part's like not super useful as like a concept.
It's not-
So we're not going to talk
You
about
have to
it.
start that linear sweep at the right place, though. Like the closest.
All right, breaking news from
At the point you
Butetown.
just added.
Archaeologists have discovered a fossil remains
Well, if
of
you're adding an
dinosaurs near
arbitrary
the
point,
city.
you have to figure out where on the
General Baitazar has N soldiers in strategic locations, right, of this evacuation area. They've got to protect the evacuation area so that way people don't like rob the bones, right? The bone thieves are a real problem in Baitown. Then what happens is you have a point being protected if moving from this point to any direction
Oh, okay.
always like makes you closer to at least one soldier.
This is that exact problem that I was thinking of.
Yeah. So so you've got N soldiers, and a point is protected if like you're gonna get closer to any of the soldiers by like moving in any direction, right? So now you've got a new rookie soldier, and the what we want to know is like, hey, you know, we don't know where to put him, right? How, like, if we consider all of these like places where we're gonna put him, how like what is the area of the total like protected part? Right. So basically you have all these like these places that, like these assignments, and we want to know like, hey, if we assigned him here, right, what would be the like protected area? Yeah.
Okay, so I haven't solved this problem.
Yeah.
Can I give an idea?
Not yet.
Okay.
So the first thing we've got to do, alright, does this like this makes sense? I think this like, alright, this should be, well, yeah, this one's like well translated. There are like some of the statements, this is from like a draft of it, so I was looking at some of the problems and like some of them are a little wild, but I think this one's alright.
Wait, when we say like, oh, we're gonna place our rookie soldier here, does that persist, or is that just like?
It does not persist.
Okay.
Yeah. So that's why it doesn't work.
Mm-hmm.
So here's the thing. We need to know when something's protected, right? So let's say we've got like a soldier here, and a soldier here. And then let's go ahead and draw our little triangle. So say you're inside this triangle. In which direction can you move such that you're getting further from all three of the soldiers?
There's no direction.
There is none. Yeah. If you're
If you're like on a perpendicular or bisector of one segment, can you not move in that?
Yeah, if you're outside or you're
No.
like on the
No,
line.
if you're inside.
Yeah. If you're outside or like on the line, you can just go like this way.
Wait,
No,
what's
I
your-
think
You
Zach
get
is
closer
saying
to the third
extend-
point.
Extend that. Zach is saying, I
Zach.
think, extend that line
Well, I guess
inside the triangle.
The area is still 0, I guess.
Yeah.
Like it doesn't matter. But
It's like moving closer only requires you to decrease the distance in at least one point.
wait, no, you still move closer.
You
wait.
still move closer
Wait,
if you
okay,
go
never
around.
mind.
To the third point.
Yeah. Yeah.
It's tricky.
So there's no way if you're inside to ever like move away from everything unless you leave the plane of existence. You know that one you know that one meme that's like the political compass, and then it's like the guy in the middle, and it's just like, I just want to grill.
He's ascended.
The normal bacteria. Okay.
Right?
True.
So unless you're grilling, right, you're stuck, right? So if you're not grilling, you're kind of screwed, right? So here's the thing. That means that if you have if you have all your soldiers, we want to know the area of the convex hull, right? So this is basically, hey, add this point to the convex hull and tell me what the area is.
Wait, the convex hull.
Yeah.
Sorry. Please continue.
That's because these triangles, right? Like if you have like
These
like you can take like any like if we have like a whole bunch of soldiers, right? Let's just draw a bunch of them.
Oh, that's a regular hexagon right there.
All right. So we have these guys, and that means that our protected area. Oh man, this is really collinear.
So it's like we're like, we need to add a point to the hole, but not really. We need to
Yeah.
consider adding it.
You need to consider adding it, exactly. Okay?
Have a really gross solution.
I as well am hungry.
Alright, that's good to know. I'll keep that in mind.
Yeah. So all of these points inside here, like, are already in the hull, right? So we actually don't care about them. These soldiers are useless, and their time is wasted.
So sad.
Yeah, it's like it's a little unfortunate for these guys, right? But here's the thing, right? So so now it's like if you have like a new soldier and you put him in here, the area doesn't change, right? So that means that if you have a new soldier, we check first if it's already in the hull, and if it is, you just print the original hull's area, right? Here's the problem. if you use like whatever hack pack you have for
Point and hull.
for like adding a point to the hull, you're gonna TLE actually. Here's why. Let's add our point. Let's say we've got a point like way out here, right? What's our new hull gonna look like?
We're gonna cut out all
Like
those.
kite.
Yeah, it's a kite.
What Jacob
Yeah.
said, yeah.
So we want this
Okay,
guy's
for
definitely
five sides.
like on the hull, right? So now let's go ahead and draw like the lines to him.
Wait.
So we're gonna say like got this guy,
Well, I can solve half the problem, or like a percentage of the problem.
right? And then we've got this part of the line here.
Because like if it's in the hole already, then the area is the same, right?
Yeah.
Good goal. Alright, nice.
No,
Yeah.
nice.
Zigno.
Exactly. So these two lines here are gonna be like this is like what's like added to our hull, right? So now our hull is gonna be like this outside part plus like all this guy.
Wait,
Right?
so why would this be too slow?
Hmm?
Why is this TLE?
So here's why it's
Because you
too
need
slow.
to
If you
organize
run
it.
your add point to hull thing, you're gonna remove all your old
Oh,
ones,
okay, okay.
right?
But don't actually remove it.
What?
Don't remove it.
That's how the.
But how are you gonna find the area?
The binary search
I have
and
an
subtract the
idea.
area of the polygon from the area of the
No,
triangle.
that's the.
Hmm?
I have an idea.
What's going on?
So like if you draw a line between the two endpoints, right? You get a triangle, right?
Mm-hmm.
Like,
Yeah, that's true.
This
Yeah,
is
so
like the
you-
naive
Let's go ahead and
homework.
draw it.
So you draw that triangle.
and
I
you can
do
easily
triangle.
figure out the area of the triangle. That's
Yeah.
usually I have. Now that
Okay.
I think about it, I don't know how to figure out the area of the rest of the polygon.
So you can figure out the area of the rest of the polygon by doing prefix sums of a triangulation from some point. And then like if you know the indices of the two endpoints of the triangle, then you can like take the prefix sum of the areas to like some point and then subtract out the area of the triangle from the starting point to those two endpoints. So it's like double inclusion exclusion.
Wait.
So let's go ahead and draw this triangle prefix sum. So let's say this is our
Start from a different point that's not inside the triangle.
that's not inside the
Yeah, it's easier. You're not inside like the tangent points. Yeah, it's easier to see.
Yeah. I was gonna do this one.
So did you just go with that?
Yeah.
Oh, that makes sense.
Jamie, what are 2 words of what you're about to say?
That I watched the lecture review when Tomash was here.
Oh shit.
That's a lot of words.
And one of them, the other one was offline.
Oh. Can you please explain the solution to this problem in one word?
Convex.
So if we do our triangulation thing again, right, where we like split it up into triangles with like one fixed point, we want to know like what this area here is, right? But so what we can do is we can say like, okay, like we've got this like what's it called? We can get like we can get all of this area like what we can say is if we want to get
What's
like
that?
the entire area, right? So what we can do is like man, I really should have drawn like another thing on the wall. Oh, there's this guy. Yeah, so there's also
Like once you have these like endpoints computed.
I'm gonna make it like a little wavy.
Is it maybe? Why does it have like
It's
circular?
there.
It's
It's like within it.
Yeah, true.
Seems like.
So if you use those prefix sums, right?
can
If
do
we do like a
order
prefix
one.
sum on these like triangle areas,
Order of 1.
what we can find is like all this area.
So true.
Can you dim the front lights a little bit, Seba? I
Hmm?
agree.
Oh yeah.
It's hard to tell the difference between the blue and the black.
I'm probably gonna burp this one. Soon.
Nice.
Nice.
Oh, that's so much better.
Yeah. So we can find like all this area, right? And we can find all this area like over here on the right, right? That would be like this like tiny area. Because I drew a terrible hole, but that's okay. So we've got these guys, right? And then now, as a result, we can, now that we've got these 2 points, we can add in like the other triangle that is like, hey, let's go ahead and like take this triangle right here. Oh shit. right? So now we've got all this triangle, like all this area that's like over here, like that we're trying to not overcount, right?
So we add in the area of the triangle and then subtract out that.
Yeah. So it's like we have the area of the hull, subtract out the blue and the black, right? And then now that gives us like this red area over here.
The sliver.
Oh, okay, you can do it that way too.
Right. So we've got the red now, and then now we want to do triangle plus the red, right? Now here's the thing. Even if we've got this, right, we need to find this like top point and this bottom point, right? We've got a whole lot of queries.
Hack pack.
Hack pack, yeah. What's going on?
Oh.
It's tangent points to convex hull.
Tangent points to convex.
Damn, bro, someone raised their hands.
That's so sad. No, I was gonna say I was wondering if we could do it offline with like some like radial sweep or something.
Yeah, probably actually. But yeah, tangent points to the convex hull. So yeah, so we're gonna do this. So this binary search is like kind of interesting because it's like so we've got our hull, right? And like let's say like we've got our hull, like let's draw a new hull. New hull.
Please sing the new hull song. Oh, we can't see the bottom of that hull, by the way.
Wait, can you not ternary search this?
Princeton.
Probably. But why would you
People want
ternary
some
search
bars,
on
homie.
integers if you love yourself?
I'll start
You
you.
can ternary search, you can also binary search. Or sorry, that's not, no, if you can binary search, I mean, that's also true, but if you can binary search, you can also ternary search.
Yeah, I just generally live in fear of ternary search on integers. So
Understandable.
if it's ever avoidable, I will avoid it.
So true and base, but
Or
it's
not solve
convex.
the problem. That's also
Good.
an option.
Good option.
As we'll see in another problem I'm going to talk about.
I think you can only. True.
Yeah, you can only.
True.
You just
Maybe
can't
not.
see the whole thing.
Yeah.
Thinking
The
about it like
whole thing.
Ah.
It's funny
Got
because
'em.
those two words sound similar.
So let's go ahead and we're gonna do that triangulation again, but this time, actually, you know what? I'm gonna get another. Let's get a bigger hull. This hull is extremely tiny and
Hey, it's not
Please, please show
it's
respect
just
to
such
the
a
whole.
terrible hull.
It's about how you use it. Not about the
So
size.
true.
This hull is bigger and therefore better.
Dang.
I think the only
That's
time a
American
ternary
hull right
search
there.
turned into a binary search fails is when you have like a slope of 0 on
Yeah.
either side of the.
Yeah.
It doesn't have to be convex, I think.
Yeah, it's like if you can ever have like values being the same and it's not like at the bottom or the top, like whatever you're trying to like get to in the ternary search, then it can fail.
Yeah.
So we've got this, right? Let's go ahead and draw our triangulation. But this time we're just gonna draw the lines like out. Actually, we're not gonna do that. What was I gonna do? Oh yeah, I remember what I was gonna do. Damn, okay. That line's out there and confusing. Oh well.
It's out.
Oh.
So what we're gonna do is we're gonna find like the lower tangent first, right? So what we're gonna do is let's go ahead and draw like these lines, these like Beyblade lines that come out from each of these like
Beyblade, let it spin.
each of these like edges on the hull.
Rip.
I was about to say that.
And we got this guy.
The shape being rotated right now before our very eyes.
For our very own.
Can't believe we're rotating shapes.
And this one. And then let's get our first one on. And ignore my cringe line.
Wait, here makes sense to do a radius.
So here, if we fix this point, right, and we have like say our query point over here, right? Let's say we're like out over here, right? What's our lower tangent gonna be?
Oh, so that's sick.
the triangle.
It's the first line that you're above, or the
Yeah.
last line that you're above.
Exactly.
It like, depends on what you.
So if you put a point like in any of these like zones,
Super sick.
right? If you put a point in any of these zones, that means that your lower tangent is gonna be like the point that like the last point on this line, right? So this guy's tangent is gonna be actually like out here, right? Like the lower tangent.
This almost is that radial sweep right here you were saying.
And then you could do the same thing, but just do the
Because this
Beyblade the
was-
other direction.
Yeah,
It's
you
a
Beyblade
lot.
the other way for the upper hole. So so we can go ahead. Yeah, if you extend out all these guys, this is how you get like what your tangent is, right? So then what we can do is like we can do a binary search on our hull, right? And we have like this point, right? And we can see we've got our previous point. Like okay, actually, let's say like we're considering like this point, right? We want to know if like the point is like in here, right? Well, we've got this vector, and we have this vector. So we can say, hey, like, is like the point gonna be like above like this line right here, right? And if it is like or if it's like above this line right here, like the one that's like me to like my next person, if it's above this line, then it's definitely not in this area, right? So you can like scooch up in the binary search. And if it's not, then it might be here or it might be like below, right? So you do like the same binary search. So it's like the first like side of the convex hull that like fails this check is like here, right? And so this is binary searchable because like so it's like you know how like our lines are like going like when you go on the convex hull we're going down and then we're going up, right? But the thing is, if we're going like down and then we're going up, that means that our slopes are always like increasing. Like our slopes are always moving in one direction. So it's like if you're going down and then up, that means that your slopes are moving like this.
We can't see that.
Right? Oh, sorry. If you're going down and then up, that means your slopes are always going like this. Right? So if you can like ternary search it, then you can binary search on like its derivative basically. And so in this case, the derivatives are basically like these lines, right? So yeah, it's like an interesting way to like think about it because it's like yeah. So to find like these tangent points, you can like binary search on these like outside lines, get the lower tangent, get the upper tangent, and then now we've got our points, right? Now that we've got our points, we can go ahead and like do our triangle magic that we did over here, right? Like all this. Yeah. And so where's I have the output here. Yeah, the output is just like just dump out like the area, like dump out the area here to 1 decimal place because like the area is always like it's integer coordinates, so it's 0 or 0.5. Yeah. What's going on?
Oh, so for the binary search, do you like you always have to have like a low and a high. Is the low like the lowest slope of all of those lines? Or
You can say like if we fix like this guy here on the left, right? You say like the low can be like you can do the low as like the first one and the high as the last one.
oh, and you know it's there's like it's gonna be like it's first gonna have the point like above that. Like,
Yeah,
so
exactly.
And then have it below.
Yeah.
So then.
Because
no
by
matter
this point
which
you've
one's
already
that.
checked that it's not in the hull, so like that's fine.
Yeah.
Because you have to check if it's already in the hull. Because if it's already in the hull, then you just print out like the original area, right? So you can just start like with your low being like this line and the high being like this line.
It'll just work no matter.
Yeah.
Damn.
Which is pretty interesting. But yeah, this looks like a James Bond like you know like the one where it looks like a straw and he's like pew. You know, it's a James Bond lecture is the real
The shuriken.
yeah.
This looks like a camera shutter.
Yeah, it
This
looks
is
like,
like we're playing balloons tower.
Yeah,
defense.
that's what that is.
It
Also.
does, actually.
Yeah. But yeah, so any other questions on this one? Alright. Yeah, this one's really cool. This one was from, the Tamash camp that was here like 2 years ago. yeah, that one was that's a nice problem. I've got another problem for that set. Well, that was when it was written. Like he brought it like
I wrote this one.
yeah.
Solve this one. I wish I did. I said I solved this one.
When it was
This
written.
one,
Oh,
Dragon
wish I didn't.
and the Knights.
Dragon these nights.
So we've got this guy. This guy is the Dragon of Wawel Castle. Actually, how long are we going till? 30 or 45?
I know the solution.
40? I'm gonna talk about this one if we have time.
What?
I don't think it's.
Sorry.
We
There's
just
a
got
better
blue
problem
balled.
to talk about.
Dang.
Sorry. Yeah, there's better problems to talk about.
What?
Yeah.
For the UCL varsity programming team?
Yeah, this one's one that you can upsolve.
Okay.
What do you mean this is one that I can upsolve? I can upsolve all these problems.
I'm saying you as like the group.
At least let the lecturer lecture. Okay.
Alright.
Well, yeah, I guess. But I kind of like
So-
the interactive.
Hey Andy. So let's talk about this other one. Alright, so this one's a problem Travis wrote, and I don't have a statement, so you're gonna have to write it here. So, there's like a bunch of races going on in, I don't know, wherever the races happen, right? So you have like N race cars. And then what's gonna happen is each car has like VS and like VC. And this is like speed on straights. And then this is like your speed on curves. Right? So each car has like a speed that like they go for like on straight like parts of the track, and then a speed like for like curved parts of the track, right? And so you've got all these cars. There's like 10 to the 5th of them, right? And then now here's the thing: we've just designed a new track. We out here at a track makers incorporated have designed a new track, right? So we've got like it's got like some segments, right? And some of them will be curved, right? But then other parts of it will
Oh. That's a bit of a brutal turn.
It's the Miami Street Circuit.
Holy, look at that non-differential track. Holy shit.
yeah. Good luck right here. Right?
What's the race?
So you've got this track, right? And we've got the length on the straight and the length on the curve, right? We've got the overall length of it, right? And we want to know, all right, new track, right? It's crazy wild, right?
That's insane.
Who are you betting on, right? You want to know who you're betting on, like on this new track. No one's ever raced on it before. You know, the meta's fresh, right? And yeah, you want to know who would win. And like if like multiple people like might like tie like based on like your data, then just print any of them, right? Like they're all equally likely, right? So yeah, so that's like and so we have like a bunch of queries of like, hey, we've got this new track, right? We've got a bunch of queries and we've got like 10 of the 5th of these guys. And we want to answer all these. And so this is like yeah. Does this make sense? Because I just wrote the statement.
Wait, how, we have
Wait, what?
10 to the 5th tracks?
Yeah.
Okay, and 10 to the 5th race cars too.
Yeah, and
Okay.
you want to know like for each track, like how many, like which car's gonna win, and then you can print any that like would be good.
Okay.
Yeah.
Was the third track, is it just defined by its length, or, like, in the problem, how is the track defined just by the length?
Yeah, just the length of the straight.
Yeah, yeah. You're just giving the length. You don't actually have like the polygon because like we love you.
Also doing that early.
Yeah.
Okay, so it's like you have this line with where the slope is like if you plot the curve on the x-axis and straights on the y-axis, then all the cars are points. And then track is a line where it's like the slope is like the straights divided by curves or whatever. And then you want the closest point to that line. Is that?
interesting way to frame it. I think that's equivalent to what I'm gonna do it, but I'm not sure. Interesting. I'll think about it. Yeah, it's like actually that's the same thing as like that. That's what I'm gonna say. So
I still don't know how to do that though.
Yeah,
There's lots of queries.
Yeah, so we've got like these guys, right? So let's figure out for a person, right? Like how like what their time on the track is, right? We so your time on the track is gonna be like length on the straight divided by like your speed on the straight plus length on the curve divided by your speed on the curve, right?
Wow.
So this guy here is gonna be your this is like your time, right? So we want like the minimum time, right? So if we've got this, right? One way we can frame this is gonna be a little wild, okay? So we can frame this as like length on the straight times 1 over like speed on the straight plus length on the curves times 1 over speed on the curves, like this, right? So then this is going to be your dot product. Length on the straights, length on the curves, dotted with 1 over speed on the straights, 1 over speed on the curves. And so now what we have is we have a bunch of race cars, which each race car is one of these vectors, right? And we want to know for each of our tracks what is like the minimum dot product, or like who creates like the minimum dot product, right? So so this is our problem now. It's like dot product optimization, which is on Spot.
What the fuck?
Yeah. Yeah, this is like a thing on Spot. I don't think this is actually the problem Travis wrote originally.
It's not.
But this is like a way to solve this problem, and there's like another way to solve his original problem, but this one's a really close up problem.
Wait, what?
This is not
Yeah.
Wait,
the
is
original
this the
problem.
problem that Travis wrote?
It's a remix.
It has
It's
the
a
same
spin-off.
flavor text, but none of the same problem characteristics.
Yeah.
'Cause it's a completely different problem.
So who came up with this problem?
Me.
Nice.
Yeah.
That's a really good problem.
Yeah, so we want to put this one in the camp, but this one's really nice. I really like this one because here's the thing: we want to minimize this dot product, right? So we have all these vectors, and then we have a query of like some other vector, and we want to know what the minimum dot product is, right? So let's think about, hey, how are we going to do this, right? So say we've got like our query. That's going to be like let's say our query is going to be x and y, right? Actually, no, we're not going to do that. We're just going to use the original variables that we used, right? So here's the thing: we've got this, right? And we want to do like minimum dot product, right? So if we look at this, right? Like at this like version of the equation, right? We can say like, okay, like one thing we can do is like, all right. So let me backpedal, right? The problem right now that we're facing is that because we're multiplying like both of these components by something, because we're like multiplying both of them by something, we can't just do convex Hull trick, right? Because convex Hull trick is like mx plus b, right? But then this is like mx plus by, right? So this is the problem we're facing with, right? We have this, but convex Hull trick lets us do this, right? So we have to figure out how, like, if we want to use convex Hull trick, maybe we can manipulate it in some way to do that, right? So the way, do you have an idea?
Me?
I thought someone was yeah, what's up, Mindy?
What if you just divide by y?
Exactly, bingo. You're gonna take all this,
What the?
and you're gonna say this is all equal to 1 over y, or actually it's gonna be,
M
yeah,
over Y.
it's y times m of x over y plus b. Right? Like we can divide everything by y and then multiply it in at the end. Right? So now, like the x that we're querying in our convex hull trick is actually like x over y. And so now this part on the v is still multiplied by 1. And then whatever answer we get back from the convex hull trick, we can just multiply it by the y. Which is pretty crazy. Because like in the track, right, we don't actually care about the length of the straights and the length of the curve. We care about like the ratio of the two, right? Because if you have a track that's like some length on the straights and some length on the curve, and you multiply it by like some constant, you make it bigger, you make it badder, you make it bigger than any track that's ever existed before,
But
same person's gonna win, because it's the same like ratio of the straights and the curves. Yeah?
No, I'm just asking.
Oh yeah. So it's like we don't actually care about the actual like total length. We only care about that ratio. So it's like that's how like this makes sense. All right. If we want to extract the time, we can do that by multiplying in like our y in at the end. So for our original equation, let's go ahead and do it like that, right? So we can go ahead and do that over here and say, okay, we've got length of the curves times 1 over speed on the straights times length on the straights divided by length on the curve plus 1 over speed on the curve. Right? And so this is like our x for convex hull trick. This is our m, and then this is our b. Right? So we can throw all of our race cars into convex hull trick, throw in like an extra thing for like an ID of like who we are, like which car is this, right? Query convex hull trick and get back our answer and see who like the min is and print that out.
But does your convex hull trick, can I add the times y in there, or like what do I have to do?
Yeah, so this part here is like a part of our like this is a part of our query coordinate, right? So it's like in the convex hull trick, we only actually give it like this x coordinate.
And right? It's guaranteed when I multiply by L's, like it doesn't go like
no, because we're just like multiplying like any line that we would get, we would multiply it by the same amount.
Oh, we're doing this okay, per track.
Yeah. Like we've kept all like
so
we put
it's
all
the same for all of the points.
Yeah.
So the convex hull is on the race cars.
Yeah, the convex like the convex hull trick, like what we insert into the convex hull trick is going to be lines of the form like 1 over vs times m or times x plus 1 over vc. Yeah.
Like what is the convex hull trick?
Like what like the trick is?
Yeah.
It's basically a data structure that lets you store lines like this, and then you can query an x coordinate, and then it'll tell you like what the minimum or like maximum line at that x coordinate is.
Okay.
Right? Yeah. I talked about it a bit before. It's like and so this like we put all of these lines from all of our race cars into our convex hull trick like this, and then now we can go ahead and query it with our tracks, and then we get our time like this. It's pretty nice. I like this problem a lot. And so you can do like this dot product optimization, which actually comes up surprisingly often in these geometry problems. Like there's a lot of problems that you can reduce to like dot product optimization, because you can say like say you want to maximize or minimize the cross product, right? Like the cross product of like two things is like if you've got like A, B, and then we've got like cross like X, Y, right? If we've got this guy, then our cross product is going to be AX minus, or not AX, sorry, AY minus BX, right? But that's the same as just saying like AB dotted with Y negative X. And this is just like rotating our original like vector 90 degrees, right? So it's like if you have like if we have like our our coordinates here, right? And we have maybe some point here at like x, y, right? So if this is our x in the red, and then this is our y, then we're going to negative y, or we're going to y for the x coordinate, right? So that's going to be here. And then, y, and then negative x. Did I do it wrong?
Yeah.
You
Y
do
is
y
supposed to be
negative.
Oh.
to the right.
Yeah. So it's going to be like this. This guy here, and then negative x like this. Let me just draw it like over here. Like that. And so this is our new point. And so if we draw a line like this, and then draw a line like this, you can see that this is like 90 degrees.
So true.
Right.
Negative
So,
90 would be more
or
specific.
yeah, like negative 9, or yeah, whatever. It's like you're rotating it by 90. You can like flip it by -1 to get the other one. But yeah, like when you take the cross product, right? What we can do is we can like just take our point, rotate it 90 degrees, boom. Now we've got dot product. Use your dot product optimization idea. Right.
That's cool.
So yeah, you can solve a lot of like problems. Like when you have like when you have stuff like this, right? Like stuff like this. If you can frame it like this and then try doing like some dot product optimization, like there's like lots of stuff you can do like that. And a lot of times it's not intended, but you can still do it because it's cool. So yeah, so that's what I wanted to talk about. I hope you liked it. That's kind of all I've got.